Well, I want to visit with you briefly about some special conditions, and the first one is called zero force members. So we have a truss here that's loaded with a force, and let's say that there is some tension perhaps in those two members, and then there's also another member that's attached right there. So let's draw a little free body diagram of that one. Let's just do that. Let's say that this one is in tension and this one is in tension, and we have a force pulling this way. Notice that these two are 180 degrees apart. We call that collinear. If they are in tension or compression, doesn't really matter. If I pull with some force here, or even push with some force, wouldn't you expect that it might push that joint out of place? It might pull it this way and displace it that way, or if you're pushing, it might do that. Well, let's imagine if they have two people holding on to a string, and if you push down with some force, wouldn't you expect that there might be some displacement? In other words, what you've done is displace it from its equilibrium position. And when you move it out of its equilibrium position, you have broken the rules. You can't have things that move out of position if which means they are not in equilibrium. So what our rule says is that there is no value of P or any value of theta to leave this joint in equilibrium. In other words, the only way for this to work is if the P has no force, or it is a zero force member. And it doesn't matter what the angle is. Over here you have the similar kind of situation, whether it's pushing or pulling at a different angle, it doesn't really matter. P has to be equal to 0 in both of these cases. So what we can do is then label this member as a zero force member. By observation, if you look at a joint, if they are 180 degrees apart, and if there are not any forces applied out here in any direction, if it only has a member applied or a member attached, then that member is a zero force member. The other condition for zero force members is if they are not 180 degrees and there are no forces attached. For example, out here I have this one going this way and this one going this way. Clearly they are separated by an angle that is not equal to 180 degrees. If I draw the free body diagram of that situation, and let's just say that there's a force going this way and a force going this way, imagine how this could possibly be in equilibrium. In other words, there could be components, or there would have to be components in this direction and this direction, meaning there's a y component here, but because there's no y component associated with this member here, there can't be any force in these members for it to stay in equilibrium. So our rule is if two members have an angle greater than or not equal to 180 degrees and there are no other forces attached, then both the forces are 0. So I'll call that also, by observation, those are both zero force members. And I call that just kind of hanging out there. If there had been a force attached like this, then they would not be zero force members. But if there is no force applied out there, then they are zero force members. Also, again, if I put a force down here, that doesn't affect it. They are still zero force members. The other special condition is called collinear pairs, and if you happen to have a force attached at well, it doesn't really matter. It can be any members or any forces at a joint. If they are if they are opposite each other, meaning collinear, then the force in the other right opposite it have to be equal to each other. They have to be equal to each other. So let's just look at this joint right here. If I say that there is a force, and I'll call this P1 and P2, and we'll call this T1 and something here called T2. Because what we know about pulling things out of position or out of joint, if I'm pulling down with a force of 600, because this is lined up, it's collinear, therefore T2 has to be equal to 600. That's the only way for this member, or excuse me, that joint to be in equilibrium. We do not have enough information in this picture to solve for both P1 and P2. However, we do know that they are equal to each other. They have the same force. If you happen to have something like this, where you have a 600 going down and then you have two forces up here, these are not collinear, meaning you cannot say that this member is equal to this member, or that this is equal to either one of those two members. You cannot say that. Only if you have two that are crossing, and it doesn't matter which. They could be at other angles as well. In other words, you could have these two going this way, and maybe these two going that way, and you'd still have collinear members or collinear pairs. But again, this one does not qualify. So if I go back to our original picture of what we just looked at, by observation, we've said that those are 0 and these are 0. Therefore, we can, again, by observation, say that this member is equal to this member, and we call those concurrent. And now again, if by observation, if this one is a zero force member, then that means this member is equal to this member, and so well, that one is also concurrent. So in other words, these three are equal to each other if these two are zero force members. Well, let's walk through how to solve one of these problems. Again, this is just a little more complicated. We have a truss here that's loaded with a couple of forces. What we've decided is that we're going to draw and find the reactions first. So I'm going to put an AY and an AX right here, and I'll put a BY and a BX. All right, let's keep it together before we draw a joint and see what we can discover. Let's sum the moments about A and see what we get. Sum of the moments about A. I have these two forces times their lever arms. BX goes through A goes through A, BY has this lever arm, so I'm going to say that BY is equal to negative 1400. In other words, I drew that arrow incorrectly. But now I can sum the forces in the y for this whole structure. So AY plus BY is equal to 0, and I can see that AY is 1400 drawn correctly in that orientation. All right, how do I keep on going? Do I have enough information to solve for AX and BX? And the answer is no, not quite yet. We have to move to a joint. So let's go to joint A and see what we can discover. So here's joint A. I have an AY, which I've already got, an AX, which is still an unknown. I'm going to draw force AE as a compression member, so I'm going to do that, AE, pushing in. And that's a pretty good guess, because I know that if it's pushing in toward that joint, there has to be a reaction pushing back. In other words, there is a reaction, because this is a two-force member. AE is, or we'll just call it A, is going backwards like that. There's a relationship, because this is a two-force member. There's a relationship between AX and AY. So let's look at the geometry. If I were to look here, this is 6 meters on this side and 4 meters on that side. If I can cut this in half, we could say that this is a 3, 4, 5 triangle. Therefore, again, we know that AE is a two-force member. I can, again, by observation now, put some relationships between AX, AY, and AE. And that's what this is. I know that AY is to 4, in the same way that AX is to 3, in the same way that AE is to 5, which is what I've got there. And by doing that, because I have AY, I can solve AE is equal to 1750 in compression. I can also use this with an angle, or I can just keep with the 3/5, 4/5, 5/5 kind of ratio. Once I have AE, I can now solve for AX by the same thing. Once I have AX, I can go back to my original my original drawing, sum the forces in the AX, and solve for BX. So here I have now the results for the supports, for the reactions. I've got AX, AY, BY, and BX. All right, so let's move to joint B, which is over here on the side. I've already got a BY. I know that it is negative 1400. What else do I know? I do know this angle theta, and which I've solved for in the prior work. So let's go ahead and now see if I can solve for these other members. I've drawn them as tension members. I don't know if they are tension members or not, but let's see if that happens. All right, let's sum the forces in the x direction. Beg your pardon here, I have another force to draw here. There is a bx, which I've already solved for as well. All right, sum the forces in the x direction. I have this be cosine theta going in that direction, bx going in this direction. I know the value of bx, therefore I can find be. I drew it as a tension member, I solved for it as a tension member, and I got a positive number. Sum of the forces in the y. I have bc plus be sine theta plus by. By I already know to be a negative number. Solving those, because now I know be, plug it into here, and I can see that bc is also a tension member, positive. All right, let's move to joint E. Let's go back and just look at our main picture just to start with. Joint C. Here I have the 900 Newton force, and it's got these three forces coming in. So let's go ahead and look at that free body diagram. This is an example of collinear pairs. If I have a 900 here, again, sum of the forces in the x, I can see that EC is equal to also 900 pushing in toward the joint. That is 900 in compression. They are collinear. You can solve them with that, sum of the forces in the x equals 0, or you can, by observation, know that that's the case. Again, if these are collinear, then these are collinear. And again, by observation, I know that CD is equal to BC. If BC is in tension, CD is in tension. I can also know that these are in the y direction, but I can see that CD is equal to 800 in tension. All right, the last joint we want to look at then is the top joint. Let's go back and look at the total picture just real quick. It's right up here. You can see that there's a 600 applied. I've already solved for this one. Now let's see if we can solve for that one. All right, so here we are. We have a 600 newtons coming in. I have CD as a positive in tension going down. I'm drawing this as a compression member going up. I do have my angle theta, which is, let's see, this is going to be angle theta, I believe, up there. Is that right? Yes, I think so. So that gives us then ED cosine theta minus 600 has got to be equal to 0. And I can solve then for ED is equal to 1000. Anyway, that gives you a step-by-step process on how to walk through the entire structure and solve for any of the unknowns using the method of joints.